The Gravity Recovery and Climate Experiment, a joint mission of NASA and the German Aerospace Center, has been making detailed measurements of Earth's gravity field anomalies since its launch in March 2002. Gravity is determined by mass. By measuring gravity anomalies, GRACE shows how mass is distributed around the planet and how it varies over time. Data from the GRACE satellites is an important tool for studying Earth's ocean, geology, and climate. GRACE is a collaborative endeavor involving the Center for Space Research at the University of Texas, Austin, NASA's Jet Propulsion Laboratory, Pasadena, Calif., the German Space Agency, and Germany's National Research Center for Geosciences, Potsdam. The Jet Propulsion Laboratory is responsible for the overall mission management under the NASA ESSP program. The principal investigator is Dr. Byron Tapley of the University of Texas Center for Space Research, and the co-principal investigator is Dr. Christoph Riegber of the Geoforschungszentrum Potsdam. The GRACE satellites were launched from Plesetsk Cosmodrome, Russia on the Rocko launch vehicle on March 17, 2002. The spacecraft were launched to an initial altitude of approximately 500 kilometers at a near-pole inclination of 89 degrees. The satellites are separated by approximately 200 kilometers along their orbit track. GRACE has far exceeded its designed 5-year lifespan. As of November 2012, the GRACE spacecraft are expected to remain in a slowly decaying orbit until 2015 or 2016. Its successor, GRACE Follow-On, is expected to launch in 2017. Discoveries and applications. The monthly gravity anomalies maps generated by GRACE are up to 1,000 times more accurate than previous maps, substantially improving the accuracy of many techniques used by oceanographers, hydrologists, glaciologists, geologists, and other scientists to study phenomena that influence climate, from the thinning of ice sheets to the flow of water through aquifers and the slow currents of magma inside Earth. Measurements of the amount of mass involved provided by GRACE help scientists better understand these important natural processes. Oceanography, hydrology, and ice sheets. GRACE chiefly detects changes in the distribution of water across the planet. Scientists use GRACE data to estimate ocean bottom pressure, as important to oceanographers as atmospheric pressure is to meteorologists. GRACE data are also critical in helping to determine the cause of sea level rise, whether it is the result of mass being added to the ocean, from melting glaciers, for example, or from thermal expansion of warming water at changes in salinity. High-resolution static gravity fields estimated from GRACE data have helped them prove the understanding of global ocean circulation. The hills and valleys in the ocean's surface are due to currents and variations in Earth's gravity field. GRACE enables separation of those two effects to better measure ocean currents and their effect on climate. GRACE data have provided a record of mass loss within the ice sheets of Greenland and Antarctica. Greenland has been found to lose 280 plus or minus 58 GT of ice per year between 2003 and 2013, while Antarctica has lost 67 plus or minus 44 GT per year in the same period. These equate to a total of 0.9 millimeters year of sea level rise. GRACE data have also provided insights into regional hydrology inaccessible to other forms of remote sensing. For example, groundwater depletion in India and California. The annual hydrology of the Amazon River basin provides an especially strong signal when viewed by GRACE. A University of California, Irvine-led study published in Water Resources Research on 16 June 2015 used GRACE data between 2003 and 2013 to conclude that 21 of the world's 37 largest aquifers have exceeded sustainability tipping points and are being depleted, and 13 of them are considered significantly distressed. The most overstressed is the Arabian aquifer system, upon which more than 60 million people depend for water. Geophysics. GRACE also detects changes in the gravity field due to geophysical processes. Glacial isostatic adjustment, the slow rise of land masses once depressed by the weight of ice sheets from the last ice age, is chief among these signals. Geosignals appear as secular trends in gravity field measurements and must be removed to accurately estimate changes in water and ice mass in a region. GRACE is also sensitive to permanent changes in the gravity field due to earthquakes. For instance, GRACE data have been used to analyze the shifts in the Earth's crust caused by the earthquake that created the 2004 Indian Ocean tsunami. In 2006, a team of researchers led by Ralph von Fries and Laramie Potts used GRACE data to discover the 480-kilometer wide Wilkes Land crater in Antarctica, which probably formed about 250 million years ago. Other signals. GRACE is sensitive to regional variations in the mass of the atmosphere and high-frequency variation in ocean bottom pressure. These variations are well understood and are removed from monthly gravity estimates using forecast models to prevent aliasing. Nonetheless, errors in these models do influence GRACE solutions. GRACE data also contribute to fundamental physics. They have been used to reanalyze data obtained from the LAGEOS experiment to try to measure the relativistic frame dragging effect. Spacecraft. The spacecraft were manufactured by Astrium of Germany, using its Flexbus platform. The microwave RF systems, and attitude determination and control system algorithms were provided by Space Systems, Laurel. The star cameras used to measure the spacecraft attitude were provided by Technical University of Denmark. The instrument computer, along with a highly precise blackjack GPS receiver and digital signal processing system, has been provided by JPL in Pasadena. The highly precise accelerometer that is needed to separate atmospheric and solar radiation pressure effects from the gravitation data was manufactured by ONERA. Measurement principle. GRACE is the first Earth monitoring mission in the history of spaceflight whose key measurement is not derived from electromagnetic waves, either reflected or emitted by or transmitted through Earth's surface and/or atmosphere. Instead, the mission uses a microwave ranging system to accurately measure changes in the speed and distance between two identical spacecraft flying in a polar orbit about 220 kilometers apart, 500 kilometers above Earth. The ranging system is sensitive enough to detect separation changes as small as 10 micrometers over a distance of 220 kilometers. As the twin GRACE satellites circled the globe 15 times a day, they sense minute variations in Earth's gravitational pull. When the first satellite passes over a region of slightly stronger gravity, a gravity anomaly, it is pulled slightly ahead of the trailing satellite. This causes the distance between the satellites to increase. The first spacecraft then passes the anomaly and slows down again. Meanwhile, the following spacecraft accelerates, then decelerates over the same point. By measuring the constantly changing distance between the two satellites and combining the data with precise positioning measurements from global positioning system instruments, scientists can construct a detailed map of Earth's gravity anomalies. Instruments. The two satellites constantly maintain a two-way, K-band microwave ranging link between them. Fine distance measurements are made by comparing frequency shifts of the link. The micrometer sensitivity of this measurement requires accordingly precise measurements of each spacecraft's position, motion, and orientation to be useful. To remove the effect of external, non-gravitational forces, the vehicles use sensitive superstar electrostatic accelerometers located near the respective centers of mass. GPS receivers are used to establish the precise positions of each satellite along the baseline between the satellites. The satellites use star cameras and magnetometers to establish attitude. The GRACE vehicles also have optical corner reflectors to enable laser ranging from ground stations. Data products, CSRGFZ, and JPL process observations and ancillary data downloaded from GRACE to produce monthly geopotential models of Earth. These models are distributed as spherical harmonic coefficients with a maximum degree of 60. Degree 90 products are also available. These products have a typical latency of 1 to 2 months. These geopotential coefficients may be used to compute geoid height, gravity anomalies, and changes in the distribution of mass on Earth's surface. Gridded products estimating changes mass in terms of equivalent water height surface are available at JPL's GRACE Dallas. GRACE follow-on. The Geoforschungszentrum Potsdam has announced a follow-on of the GRACE mission. GRACE-FO mission will be a collaboration between GFZ and NASA and is scheduled to be launched in August 2017 on a DNEPR from Baikonur Cosmodrome. The orbit and the design of GRACE-FO will be very similar to GRACE. The distance between the two spacecraft of GRACE-FO will be measured with lasers. As a technological experiment in preparation for future satellites,